Okay, I couldn't really wait, so let's just continue. So we have this, and what we want to do is to render it independently of the screen size, and we actually want to make some more sense of these numbers, of this coordinates. Currently it's in clip space. It doesn't really make sense. It's not something in the game world, it's just something on the screen in a very weird way, so not even like pixels or whatnot. So let's say that those are meters, like game units, you know, meters in the game. And to actually change this to back to the clip space and to the well, ultimately the screen coordinates, to the screen space, we need to do projection. And projection is basically a transformation of these coordinates that we give using some matrices that we can easily provide. I'm not really good with them. As usual, I know the concepts and I barely know how to use them. But basically we just need to multiply some matrices with vectors to get new vectors based on the multiplication result. And thankfully Odin standard library provides everything that we need for that, which is here in math.linalg. So linalg is, of course, stands for linear algebra, and it contains a lot of cool functions. For example, it contains linalg matrix perspective. So this is for perspective projection, which is exactly what we need to have a 3D view into the world, which would help us making sense of these numbers as meters or whatever, and help us get to be independent of the screen size. So let's just do this, exactly this. Let's create a matrix, perspective projection matrix, with FOV. So this is where we would set up FOV, let's say 70 or something. Then the aspect ratio is what would, of course, control the stretching or not stretching. And since we want to maintain the same values, not depending on the aspect ratio, we want to pass the aspect ratio here. And for that, it's very simple. The Sokol application module provides our width as a float, and we can divide this by height as a float. So this would be the screen width and height. Then it needs to provide our clip coordinates for near clipping and far clipping, far planes and near planes. I can't say much about them, but everything that is closer than near will be not visible, and everything that is further than far will not be visible as well. So the near value should be something small, but not 0, I think. For reasons I'm sure graphics programmers can tell us. And the far should be something large, let's say, yeah, 1,000 meters will do. And the z-axis is basically whether we want to have forward as a plus z or a minus z, and by default it's minus z, I believe, because this flip z-axis is true. For some reason, I believe this is called right-handed coordinate system, so we just need to keep in mind that forward is minus z. So now we can create this matrix, and Odin will complain about that the result is not handled. So this will be projection matrix. Normally, in the how we use it in the shader, in the 3D render especially, what we use is called MVP, so model view projection matrix. The projection matrix controls how do we project the 3D into the screen space or the clip space. Then the model actually controls the translation and rotation and scaling of a specific model, and the view is the same of the view, so basically of the camera. And we will use all three of them, but let's start with the projection. So we need to pass this for the to the shader, and this doesn't depend on a specific vertex, but rather on a draw call. So this is like the same for the draw call, which means it's another uniform, so let's specify it. And we need to use this not in the fragment shader, but rather in the vertex shader, so it's a uniform of, let's say, vertex params, so we can specify multiple stuff here. And we want to just pass 4x4 matrix of MVP here. Now if we try to compile, first we of course will get a syntax error because I'm so good. I'm so used to Odin that doesn't need a trailing semicolon, but GLSL needs, so let's provide it. Then it will complain that we need to specify explicit binding slot for it, so let's just copy it from those guys. And now we actually have it, right? Now we need to use it, and to use it we want to modify the position, and what we do is just multiply our vector by this matrix. And this is everything that we need to do in the shader. Now it will complain that the uniform is missing, thank you Sokol. And we need just to pass this somehow. And again, Sokol provides us with a handy structure called VS_params. It's called like this because I called it VS_params here. I could also call it VS_params in lowercase, I believe. But it will be translated into the Sokol style of, I think it's called other naming or something. And it will also provide us with a uniform binding slot for VS_params. And this is kind of the same as image binding slot and the simpler binding slot, but the uniform bindings are done with a different function, so it's it's a slot for the uniforms, which we do with apply uniforms. So we need to provide this UB VS params, then we need to provide the data, and the data is again this range, which is a pointer and the size, if you remember, like this one, right? And the pointer, I don't really want to allocate memory on the heap or whatever. We can just say that I want to create the params as a variable on the stack. So VS params, VS params should be just an MVP, right? It has it here. And that would be our projection matrix like this. So now it complains about some stuff here. First, that we want to pass it as a range, and we need to again specify the whole PTR and size here. So I don't really like this internals here. Let's create a function sgRange. Let's actually use it like this. But the one that we have here is intended to work with slices, so let's have another version of it. So that would be range from slice, and that would be a range from struct, and that would say, all right, I want to have a random type, which is actually using this intrinsics, I believe. I can never spell this correctly. Yeah. This is basically just a little bit of polymorphism on the Odin side. So we want to create a range from struct, and we want to constrain our type with that it is a struct and not an array, so it will know which function to choose because we are gonna use this explicit overloading feature. So type is, oh my god, I can't type, is struct, right? And we do this. Now we can just say sgRange in general is a procedure, and it's one of those. So either this or that. And this is complete garbage, so this is not correct. We want to have a pointer here, so raw data does make sense, we can just use it like this. And the size, in this case, is just size of t, because we want to pass the whole structure as a range. So now we can actually do this if we pass a pointer, and this still works. Where we use it here for slices, it will choose the other one, which is nice. We can just use a small helper function for creating Sokol ranges. Anyway, this projection matrix, now it complains that the type of whatever is returned from linalc is actually a type of matrix for whatever, which is this is built-in matrix type of the Odin language, and this is something that is very nice in the Odin language because it contains a lot of helper stuff to work with vectors and matrices. But the problem is that those fields, even though they are exactly the same in the memory, they are not specifically compatible when it comes to the type checks. So what I like to do is to define our own mat4 type, which is exactly this. It will be compatible with whatever linalc uses because it uses ultimately the same type. I just like very short names for the types that I use very, very often. And now we can say to the shader, so it would use this type instead of what it generates by default for the matrix type. And how we do this is by specifying yet another annotation here called cType. And first argument to it is the GLSL type, so mat4, and the second type is the type that we use here, that we define here, so the one to generate. And now if we do this, it will actually generate our structure with the proper type. So nice. But now, since we don't see anything, we might be wondering if we did something wrong, but we actually didn't. The problem here is that the camera is currently staying at the 0, 0 coordinates because we didn't provide any view transformations. We only provide the perspective transformation. In the perspective transformation, we'll take a look at the coordinate of the shader that we get here and see that the z is 0 and the camera is at the 0. So with this projection matrix, it will just clip it because 0 is smaller than this clip value. So what we want to do basically is to move our object, but our object is actually still considered a 2D, right? Because we only use vector 2 and we explicitly hard-coded to the 0z in the shader. So that's gonna have to be changed. So the position now needs to be a vector 3. And of course the position that we pass here needs to be a vector 3. So in the vertex data, the position is now vector 3. Alright, now the Odin language server complains about this, and now we can provide z coordinate. And if you remember, the forward is minus z, so if we move it like 1 meter to the forward, we should see it, but for some reason we don't. So that is weird. Do we actually multiply everything? Do we actually bend the uniforms? I believe we do. So what is the problem here? What if we move it to the what I think is back? Yeah, we still don't see it. That is weird. So, of course, yeah, the problem is that, yeah, we forgot to specify in the layout for the pipeline that now the position is 3. sadly, the system will not do this for us automatically, although that would be pretty cool. But I guess in real world scenarios where the vertex buffer can contain a lot of different stuff, it's kind of hard to guess just by the shader configuration what the actual layout of the vertex buffer should be. So anyway, now it should work, and it does. And now if we resize the window, it will not react right away for some reason. I guess maybe the Sokol doesn't really do the frame when we resize the window. Maybe this can be changed, I don't know. But when we do resize the window, when we finish that, we actually have the proper aspect ratio of our quad, which is nice. What is not nice is that we specify the Z coordinate here for the vertex buffer, and this is a no-go, because what this vertex buffer basically describes is a mesh, and the mesh needs to be in its own object space. So this should be 0 really, because it's relative to itself. If we want to move the object, we want to use the model matrix, and this is this M part of MVP. And thankfully, linalc provides a lot of cool functions to construct the model matrix. For example, it can construct a matrix from translation, or from scale, or from rotation, or from yaw and pitch and roll, so another kind of rotation, from quaternions, from TRS, I believe, which is your transform. Like if you use to Unity, this is what would be your transform, so the translation, rotation, quaternion, and the scale, and all the other stuff. So what we are interested is, let's call it mod, or maybe we should just call it P and M, because MVP, you know. Let's just use something very simple like linalc matrix for translate. We can use this F32 version, and we just want to translate here by -1.5, right? So to the front. And now if we multiply P by M, by the way, the matrix order is very important, because you can't just change them around, and it should be that the last matrix you want to be applied, it should be coming first, so you multiply it by whatever you want to be applied before. So that should already work, and it does. And now we can do some cool stuff. For example, we can rotate our beautiful model. For example, we can store a rotation of the model, which would be just a float, right? And we can maybe define a rotation speed of, I don't know, 90 degrees per second. Sounds good enough. So now we want to have a rotation matrix here. And what we want to do is first rotate and then translate. That means that we need to multiply the translation matrix by the rotation matrix. So we specify it as a second operand of the multiplication, of the matrix multiplication. And we can use from yaw matrix yaw pitch roll, this one, it's really cool. And the rotation, let's rotate around the up vector, so that would be yaw exactly. So we will need to specify the rotation, and the pitch is 0. We don't want to rotate on the pitch, and we don't want to rotate by the roll. And yeah, if we run it now, it will complain about something. Mismatched matrix, because I used matrix 3 instead of matrix 4. because I'm stupid this way. Of course. Alright, now the rotation doesn't really do anything because it's 0, we didn't really change it once. So to do some animation, we usually need a delta time. In Sokol, we get this as a s-up frame duration, so that's just a float 64. We don't really need that much precision, so let's cast it to f32. And now we can just say g rotation plus equals rotation speed multiplied by delta time. Now the problem is that the rotation that these matrices expect is actually in the radians, but thankfully converting degrees to radians is a very simple multiplication, so you can just multiply it by deck to deck per rad or something. That's actually rad per deck, or you could use a function called linalc 2 degrees. Well, 2 radians, of course, because we expect radians. So now we can actually look, our beautiful model is rotating. It's very nice. We can change our yaw to roll to get rolling rotation. We can change it to pitch to get rotation around x-axis. So this is very, very nice. This is getting really 3D. Very good. Now the other thing is that we don't have is a camera control. We would like to move around, right? So let me get myself another cup of tea, and then I will come back and we will try implementing a very simple camera.